Today, we're diving into a really strange and fascinating mathematical object, the MRB constant. It comes from an infinite sum that, when you first look at it, seems like it should be complete and utter chaos. But, as we're about to see, there's a beautiful order hiding inside. Okay, so what in the world are we looking at here? This graph shows the running total of a series of numbers being added and subtracted. But notice what's happening. Instead of the total getting closer and closer to one single answer, it just bounces. It oscillates back and forth forever between two different levels. It never settles down. And right there, that's the central mystery we're tackling. If the sum never actually stops and lands on a single number, how can we possibly give it a specific value, a constant? It feels like it should be impossible, right? But it turns out there's a really clever way to think about it. To figure this out, we've got to get a better feel for this oscillation. So let's actually look at the numbers. So look at this. The first term is -1. Easy enough. Add the second, and we jump all the way up to positive 0.414. Add the third, and we're right back down to about -1 again. You see the pattern, right? The sums after an odd number of terms are all hovering around -1, and the sums after an even number of terms are hovering around some small positive number. It's like they're two separate teams, each inching towards its own goal line. And this is the absolute key. The sum never converges to one point because it's actually converging to 2 points at the same time. These are called accumulation points. And as you go further and further out to infinity, the distance between where the high bounces land and where the low bounces land gets closer and closer to exactly 1. So, if the sum has two different destinations, which one do we pick? This is where the MRB constant finally makes its entrance. By definition, the MRB constant is just the value of that upper accumulation point. The fancy name for this is the limit superior. So while the whole sum jumps around, that sequence of even-numbered sums is zeroing in on this one very specific value, about 0.187859. That is the constant.
And here is my favorite part of this whole story. This constant wasn't discovered by some professor in a university lab. It was found by Marvin Ray Burns, a guy who worked in the construction trades and just happened to be a self-taught math enthusiast. He was just playing around with these series on his computer and noticed this weirdly consistent upper limit. It's just an amazing reminder that discovery can come from anywhere.
Okay, so we've got our constant. Now, the next logical question is, can we calculate it? And the answer is yes, but oh my, is it slow. Painfully, excruciatingly slow. So why is it so slow? Well, here's the problem. The numbers that we're adding and subtracting, they get closer and closer to 1, but at a glacial pace. This means every time you add a term, the very next term you subtract almost perfectly cancels it out. You're taking one step forward and then a nearly identical step back, so making any real progress is just this frustrating, slow crawl. And this graph shows you exactly why. Look at that blue curve, which represents the terms in our series. See how it just flattens out? It's barely moving. It's crawling towards its limit. That super slow decay means each new step in the sum makes only a teeny tiny change to the final answer. And just to put a number on it, if you tried to calculate this constant the simple way, just adding up the terms one by one, what's called a brute force sum, you would need to add up over 147,000 terms just to get the fourth decimal digit to settle down and stop changing. It is an absolute computational nightmare. But luckily for us, mathematicians have found a way around this kind of problem. It's a whole field of study called series acceleration, and it's all about being clever instead of just using brute force. The whole idea behind acceleration is just brilliant. Instead of trying to walk all the way to infinity by adding millions of numbers, these methods just look at the pattern in the first few dozen steps. By analyzing the rhythm of the oscillation, how it bounces, how it decays, they can actually predict where it's going to end up without having to take the whole journey. So a classic method is something called the Euler transform. It looks at the sequence of sums we saw earlier. Then it looks at the differences between those sums, then the differences of the differences, and so on. And it turns out there's a hidden pattern in those differences that shoots towards the final answer way, way faster than the original sum ever could. And the results are, well, they're just staggering. Remember, brute force needed almost 150,000 terms for just 4 digits of accuracy. An acceleration method can get you 22 digits of accuracy using only about 60 terms. I mean, it's not even a fair competition. You can see the difference so clearly here.
On the left, that's the raw sum. It's messy, it's chaotic, it's slow. But on the right, that's what an accelerated series looks like. Look how quickly and smoothly it just hones in on the answer. That's the power you get when you spot the hidden pattern instead of just crunching the numbers. So this is a really cool mathematical party trick, but it's so much more than just a neat thing you can do for one obscure constant. See, this idea of accelerating convergence is a fundamental tool. Anytime a calculation in physics or engineering or even finance involves adding up an infinite number of things that just takes too long to be practical, these are the techniques people turn to. They make calculations that would otherwise be impossible, possible. The history of calculating this very constant tells the whole story. Back in 1999, getting 5,000 digits took 2 hours. By 2007, getting 100,000 digits took a whopping 170 hours. But look at the jump by 2022. Thanks to better computers and much, much smarter acceleration algorithms, that same calculation took less than 15 minutes. And now it's even faster. That's not just faster chips, that's better math. And that's really the big takeaway here. These methods take a problem that feels like an infinite, painful crawl, and they turn it into a short, manageable sprint. It's the difference between a problem being theoretically possible and a problem being practically solvable. And that kind of leaves us with a final, fascinating thought, doesn't it? The MRB constant is this perfect example of a process that looks totally chaotic and endless on the surface, but it's hiding a simple, predictable pattern right underneath. It really makes you wonder, what other impossibly slow problems out there, in science, in technology, anywhere, are just waiting for someone to spot that hidden pattern and find the clever shortcut?